Yeah, if you have any questions on Fourier series definitions, and then we did two examples. If you can recall, so this was the first example. X of t is equal to sine omega naught t. So this is a single sinusoid, and this we can find Fourier series quotient uh, just by inspection. In the sense, we did not use the formula ak equal to 1 by t integral 0 to t x of t power minus j k omega naught t. We just did it by inspection. We expressed sine omega naught t as a in terms of exponentials. And then there was a second example. It also consists of all the sinusoids. Yeah, so these are not much difficult, these examples, and they are not like you can get convinced that okay, so x of t is already consisting of sinusoids, so we can always express them as a linear combination of sinusoids. So that's why we'll take one of the most interesting examples. uh, so I'll continue with with next example. This example is one of the most important and interesting examples for Fourier series or Fourier transforms, especially for Fourier transforms. So it is a periodic square wave. So let's consider a periodic square wave, which looks something like this. So this is time axis, right? And then here we have so this is plus t1 and this is minus t1 and this amplitude is 1. And let me write this as x of t, and then this is, so let's call this as t by 2, and then this is minus t by 2, and then here comes, so if this is t by 2, this should be t, somewhere here it should be t. Right, and again somewhere here it should be t. So as you can see, this is a periodic square wave. So this is t to t, and then here again, yeah, sorry, this should be minus t and minus 2t. So this level is 1, right? So this is a periodic square wave. Sorry, there should be somewhat less gap here. So this is a square wave and it's periodic. So x of t is periodic with period equal to t, or fundamental period. Yeah. So whenever we say period, generally we refer to fundamental periods, right? Yeah. And then we have to express this periodic wave mathematically. So how do we express this? Over one period, we can express this. We can express x of t mathematically as x of t is 1 for mod t less than t1, right? So if it is less than minus t1, sorry, if it is greater than minus t1 and less than t1, it is 1. So that I can represent as modulus of t, right? So this implies minus t1 less than t1. So this entire expression I can express simply as modulus of t, right? And it is 0 for t1 to t by 2. T1 modulus of t by 2, right? So what does this mean? It is 0 from minus t1 to minus t by 2. So this notation means that, this notation means that minus t by 2 less than or equal to t less than or equal to t1, minus t1, and also t less than or equal to t by 2 greater than or equal to t. So whenever I say this modulus, this means these two things. So if you simply apply what is modulus of t, then you will get these two things. So we will be frequently using this kind of notation in this course. So you better be accustomed to this kind of notation, this modulus of t, right? Yeah. So and this, as I said, this expression of x of t is only over one period. Like over one period, it is non-zero from minus t1 to plus t1. It is 0 from in this interval and 0 in this interval, right? So as it is periodic with period t, its fundamental frequency is 2 pi by t, right? Now finding AK. What are AK? Fourier series coefficients. Yeah, so in the previous two examples, example 1 and 2, we haven't used the formula required for AK. We could do it simply by inspection. Here we will do it using the formula. So if you can recall, can you recall the formula? Is equal to 1 by t and x of t e power minus j k omega naught t dt. And here there is an important fact. So in the previous class, once I wrote this integral, then I simply denoted here saying t. Then I said that this integral t something dt is equivalent to this notation t says that it is integral over one period. And then I quickly said that maybe this will confuse you, and then I changed this to 0 to t, right? Do you remember? Like if you see in the last class notes, somewhere I have written when for the first time when I defined AK, I wrote something like this: 1 by t integral t here and x of t e power minus j omega naught t dt. Then I said this notation is nothing but the integral is being evaluated over one period. And then I said it may confuse you, so let's make it into 0 to t. Okay. So why am I saying that here? Why is this becoming important here? Because here, see, if you see the waveform, here I can take the period as 0 to t, right? If you see the period as 0 to t, or you can also see the period as minus t by 2 to plus t by 2. Like this is also a period. This duration is t. Again, this duration here is 3t by 2. This is also t. So we can consider this duration as t as one period, or we can we can consider this period is also, this also as one period. This is also duration t. So which one do you consider? That's, so I can integrate over this period between 0 to t, or I can integrate over minus t by 2 to plus t by 2. Because all that I need to do is to integrate over one period. That one period is a duration of t seconds. So that duration of t seconds in this waveform, I can take it from minus t by 2 to plus t by 2, or from 0 to t, right? So if I take it from 0 to t, so if I take it from 0 to t, that the waveform will be somewhat like this. This is 0 and this is t. Whereas if I take the integral from minus t by 2 to plus t by 2, I'll get a waveform like this. If I look at this waveform from minus t by 2 to plus t by 2, so this minus t by 2, this t by 2, I'll get a waveform like this. This is much more easy for me to integrate than this waveform, right? So all that I need to do to find AK is to integrate over one period over a duration of t seconds taken anywhere on the time axis, and instead of taking that integral from 0 to t, in which case I'll have this waveform, what I'm saying is I will integrate it from minus t by 2 to plus t by 2, right? So if you have any questions, I think you can ask orally. That's what that's what I was told. So you can interrupt me and you can say something. But yeah, so otherwise I'll keep continuing. You need not wait for me to pause. Like you can say something, so I will pause and I will listen to you, and then we can go ahead again. Right? So we will integrate from minus t by 2 to plus t by 2, rather than from 0 to t. So what happens? Minus t by 2 to plus t by 2. But we know that in the duration minus t by 2 to plus t by 2, x of t for j k omega naught t dt. So this is nothing but 1 by t minus t1 to plus t1 1 e power minus j k of omega naught t dt. Is that right? Because in the duration from minus t by 2 to plus t by 2, x of t has got value 1 only from minus t1 to plus t1. So we are integrating from minus t by 2 to plus t by 2 in this integral, in this interval. In this interval, it is 1 only in this duration, from minus t1 to plus t1. That's why this is AK. So let's evaluate this. For k equal to 0, A0 will be 2 by t minus t1 to t1 dt. Right? When k equal to 0, this exponential will also become equal to 1. So it is simply 1 dt. So this is 2t1 by t. Okay. So this is equal to our A0. Let's keep it aside. Okay. So this is a simple integral. And then for k not equal to 0, what do we have? We have AK equal to 1 by t minus t1 to plus t1 minus t1 to plus t1 e power minus j k omega naught t dt multiplied by 1. So this is simply e power minus j k omega naught t divided by minus j k omega naught integral minus t1 to plus t1. So that becomes what? Minus of e power minus j k omega naught t1 minus e power j k omega naught t1 divided by j k omega naught, right? I just substituted the integrals, and then this simply becomes 2j. So yeah, sorry. So this simply becomes 2j sine k omega naught t1 divided by j k omega naught. So here there is this 1 by t, right? So this t also comes here, capital T. So this, yes, and in place of t, I can write as sine k omega naught t1 divided by k omega naught. T is 2 pi by omega naught, right? So this omega naught is omega naught. So this is sine k omega naught t1 divided by k omega naught. I'm sure this is fairly a simple integral for you to evaluate. Maybe I don't need to do every step, but anyway, this is this one. So what do we have now? So what do we have now? We have a0 is equal to 2t1 by t, and ak is equal to sine k omega naught t1 divided by k pi for k not equal to 0, right? So okay, one fact is that these Fourier series coefficients are real valued. AKs are real value, right? So that meaning we can represent AKs as in one plot, and if it is complex, so if AKs, sometimes the AKs are need not be always real valued, and then if it is complex, we need two plots to represent AKs, one for the magnitude of the AKs and the other for the phase of the AKs, and finally these AKs are discrete values AKs are defined for k equal to 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on up to plus or minus infinity, right? So these on x-axis you have k value, and on y-axis you have so let me show this. So this will be something like this. So on x-axis you have k 0, 1, 2, 3, and so on, and -1, -2, minus 3, so on. These are AK values. So it is A0 is 2t1 by t, and similarly for different values of this, you can find out this. So if you are given t1 and t values, you can accurately find out these values and you can plot it down, right? So let's do this as homework for t equal to 4t1. For t equal to 4t1, what happens? A0 is equal to 2t1 divided by 4t1, that is equal to half, and a1 equal to a minus 1. Okay, so maybe I better write one more step here, and then ak, what happens is sine k omega naught t1. T1 is t by 4, divided by k pi, and let's also do, instead of omega naught, I want to write 2 pi by t. So instead of omega naught, I can write 2 pi by t. So this pi, this t gets cancelled. So this will be sine k pi by 2 divided by k pi. Okay, this for k not equal to 0, and then you can find observe that ak equal to 0 for all even values of k. So here, if k becomes an even number, set to n, then this will be sin n pi, and sin n pi will be 0. So ak equal to 0 for all even values of k, but not for k equal to 0, right? Because 0 is also considered as an even number. But so a0 is equal to half, which is not equal to 0, right? See, simply I'm trying to explain more and more. I don't need to explain these many things, I guess. But simply what I'm trying to say is, when t equal to 4t1, we have this. This is just extending the example so that you will know how to compute the Fourier series quotients. So what I'm trying to say is, when t equal to 4t1, a naught equal to half, a1 equal to a minus 1. So I have computed it on my notes, and then I'm just simply writing that calculations. Like I'm not trying to do it again just to save time, but I'm sure you should try this at home. So a3 equal to a minus 3 equal to, okay, you can fill these things. a5 equal to a minus 5 equal to something, and it is 0 for a2, and a4 equal to a minus 4 equal to 0, and so on, right? Yeah, so this is a, as I said, this is one of the most important examples, periodic square wave. So why should we consider this as an important example? Because this is a surprising fact. Till people invented Fourier series. Okay, if you read a bit of history on Fourier series, People like Euler, way back, who is the inventor of geometry, Euclidean geometry. He also thought about Fourier series, but he didn't pursue it more rigorously. And later, Fourier, a French mathematician, he pursued it rigorously, because it is little bit surprising that a wave something like this, a square wave, has got square wave now is being represented as a sum of sinusoids, as a sum of complex exponentials, right? But you cannot see any sine wave physically if you look at the waveform. So that itself is counterintuitive when it was invented, when this Fourier series was developed. So that's one thing, and this example helps us to move from Fourier series to Fourier transforms. So the next topic we will study is Fourier transforms, and so we will and defining Fourier transforms needs some trick, like needs some clever thinking. So this example helps us in understanding how Fourier transforms can be developed based on Fourier series, right? So we are done with all the examples. Sorry, not all the examples, all the three examples of Fourier series. Now let's move to the next section. Sorry. Properties of Fourier series. So I'm as I said at the beginning of the class, I'm just moving ahead fast. And if you have any questions, you can stop me at any time. You can just raise your voice. Everything that we did till now, but what we did was, if x of t, yep, if x of t is periodic, x of t is periodic, with period t, then what we said was it can be expressed as a linear combination of, as a weighted linear combination of complex exponentials. Okay. What I found is, yeah, I should mention one point before moving on to properties of Fourier series, because your syllabus says that should be knowing about exponential Fourier series, trigonometric Fourier series, these two things. We studied exponential and trigonometric, but I haven't used the word exactly as trigonometric Fourier series. So you may be thinking that like this is something different. So let me write that out. So with period t, and fundamental frequency omega naught equal to 2 pi by t, right? So we can express, then we can express x of t as this, and this can also be expressed as k equal to minus infinity to plus infinity ak e power j k 2 pi by t. Simply in place of omega naught, I am putting it 2 pi by t, right? Where ak is 1 over t integral over one period of t, x of t e power minus j k omega naught t dt, or this can also be written as 1 over t integral over t x of t e power j k 2 pi by t small t dt. So this is called exponential Fourier series. So if you write x of t as linear combination of complex exponentials, either in the form of e power j k omega naught t, or in place of omega naught t, you simply put t 2 pi by t. Then and ak is computed as this. So this is called exponential Fourier series. So if there is a question saying that in exponential Fourier series, what do you mean by blah blah blah, like something like that, right? So then you should use this formula. If you are asked to use exponential Fourier series, you should use these formula. Either this formula is okay or this formula is okay. If you see different textbooks, say if you okay, we are following Oppenheim and Wilsky. Instead of that, maybe if you see Simon Hekin or Barry Van Veen or V.P. Lathi, then you may find another notation. You may not find omega naught, but there you may find 2 pi by t. So anyway, so these two expressions are called exponential Fourier series, and what happens is and when x of t is real, when x of t is real in the sense real valued signal, real valued periodic signal, then x of t can be expressed as this. Also we did in the last class. X of t can be expressed as a naught plus 2 into k equal to 1 to infinity. See, in the previous case, it is k equal to minus infinity to plus infinity, right? Here it is minus infinity to plus infinity. And so what we are writing now is when x of t is specifically real valued. In the previous case, there was no such constraint. Here we said x of t is simply a periodic signal with period t. X of t can be complex valued or real valued, but it has a period t. In other words, the fundamental frequency omega naught equal to 2 pi by t. And x of t here can be complex signal or real, whatever. But here, when x of t is specifically real valued periodic signal, we can express x of t as something like this, where it is ak cos k omega naught t plus theta k, or it can also be written so, where ak is equal to capital AK e power j theta k. So what is this capital AK and theta k? You simply find the small a of k and then express that in the polar form. So this is expressing AK in polar form. Or there is another representation. It can be written as a naught plus 2 into summation k equal to 1 to infinity some bk cos k omega naught t minus ck sin k omega naught t. And what are these bk's and ck's? You simply find ak and then express that as, so this so this is expressing AK in rectangular form. And how do you find AK? AK is again 1 over t integral x of t for minus jk omega naught t dt or it can also be written as x of t e power minus j k 2 pi by t small t. So this form and this form, these two are called trigonometric Fourier series. So if you are asked to use expand the signal in using trigonometric Fourier series, then you should use preferably this formula or this formula. Generally people use this formula in trigonometric Fourier series, right? So this is a summary of what we studied about Fourier series till now. We studied the exponential form when x of t is a periodic signal and x of t can be complex or real, and then we studied when x of t is specifically a real valued signal, we come up with the trigonometric Fourier series, right? So with that let's move on to the properties. Yeah, so as I said again, if you have any questions, please raise. Or these properties, what we do is we'll try to derive them one by one in a more what you call intuitive manner. I won't simply state the properties, and you should not be mugging up them. You should be able to derive them. So properties of Fourier series. So the first property is linearity. Okay, a little bit of a background, just a 1 minute background before. Why do we need to study the properties? So okay, so you will understand as we go ahead that these properties are easy means of computing Fourier series. Say for example, if you have a Fourier series for two signals, right? And then if you want to compute Fourier series for the third signal, which is a linear combination of these two signals, then you need not go from basics again. You can simply apply one of these properties and then find the Fourier series of the third signal. So these properties are extremely useful, and almost all your questions will be based on how you use the properties. So most of the times, so I'm saying most of the times, not always. Most of the times, you will be using some of the property to compute a Fourier series of a given signal. And of course, sometimes you also should go back to the definition AK, integral AK. But most of the times you will be making use of the properties. So let's start with the first property. So sorry. So give me 1 minute in writing out some notation. So we will use the following notation. If AK k equal to 0 plus or minus 1 plus or minus 2 and so on, or the Fourier series quotients of x of t, then we write as x of t double arrow Fourier series AK, right? So say x of t is there and we found its Fourier series quotients and they are AK, A0, A1, A2, A3 and A minus 1, A minus 2, A minus 3 and so on. Then we write, this is the notation for that. So in other words, the notation x of t with double-headed arrow and with two letters fs on the top of the arrow and ak denote that x of t is nothing but ak e power j k omega naught t, k equal to minus infinity to plus infinity. Or this also means that k equal to minus infinity to plus infinity ak e power j k 2 pi by t k small, right? So keep this notation in mind. We'll be keep using this notation very often. Okay, so now the first property, linearity. Let x of t and y of t consider two signals x of t and y of t are periodic with the same period of t, right? Period of t, and the Fourier series coefficients of x of t are given by ak, and Fourier series coefficients of y of t are given by pk. Then what will be the Fourier series coefficients of z of t, which is a weighted linear combination of x of t and y of t. So if we solve this question, we will derive linearity property, right? So let's do it. Like it's very simple. So I think if I give you just 2 minutes time, you will be able to do it. Like I'll be online. I'll be looking at these questions are given by AK. So this is this. So this implies that as we simply did it in the notation, this is AK e power j k omega naught t, right? So when x of t's Fourier series coefficients are ak, that means that x of t is summation ak e power j k omega naught. Similarly, when y of t's Fourier series coefficients are pk, it will be y of t equal to summation of pk e power j k omega naught. So the same thing I'm putting it here. This is x of t and then b into pk e power j k omega naught. So this is y of t. Right? So hope this much you have done, because this is very straightforward. Then let us see. Then what we can do further is, so now it is nothing but ak plus bbk k equal to minus infinity to plus infinity e power j k omega. That's it. So this I can write this simply as some ck e power j k omega naught t, where k equal to minus infinity to plus infinity, where ck is equal to aak plus bbk, So simply the Fourier series coefficients of z of t are this. So what we can write, z of t or simply what we can write as this is ax of t plus by of t is ak plus bb. So this is nothing but the property of linearity. So when x of t's Fourier quotients are ak, when y of t's Fourier quotients are bk, then a into x of t plus b into y of t will have its Fourier quotients as capital A into ak plus capital B into bk. So this is linearity property. See, you need not, as I said, you need not kind of by heart or mug up these properties, and you can derive all of them by your own, even if you forget in the exam. So in fact, one of the properties derivation is very involved. Like we'll come to that later. So the second property is time shifting. So if x of t Fourier series quotients are ak, what will be the Fourier series quotients of x of t minus t naught? So this is the question we are trying to answer. So we have x of t and its Fourier series quotients are given to us by someone, and then we wanted to find Fourier series quotients of a time shifted version of x of t minus t naught. This t naught can be positive or negative, but what are its Fourier series quotients? So this, we know that x of t is ak g power k omega naught t, and we want to write x of t minus t naught, right? So this is over k equal to minus infinity to plus infinity. And simply in place of t, I should put e power j k omega naught. In place of t here, I should put t minus t naught, right? Because here t got changed from t to t minus t naught. Here also t should get changed from t to t minus t naught. So this equals yeah. So this is simply nothing but ak e power j k omega naught t into e power minus j k omega naught t naught, right? So this simply I can write this as ak into e power minus j k omega naught t naught to e power j k omega naught t. So my Fourier series coefficients are simply these. These are the Fourier series coefficients. These are the Fourier series coefficients of x of t minus t naught. Because these coefficients multiplied by e power j k omega naught is my Fourier series expansion of x of t minus t naught. So that meaning x of t minus t naught it has got a Fourier series quotient. So ak multiplied by e power minus jk omega naught t naught. So this is time shifting property. And the importance of these properties is the same properties will hold good for Fourier transforms also later. So right now we are doing continuous time Fourier series, then we will do continuous time Fourier transforms, and these see almost similar kind of properties hold good for continuous time Fourier transforms as well. Oh, okay, okay. See, I have run out of the pages here of this notes. So this digital notes will give me only 100 pages. So I think all the 100 pages are over, but it's okay. What we will do is, yeah, these 100 pages are over. But I can save this and erase this so that. So yeah, just give me 1 minute. I'm trying to find how can I save this. So for today, let's not waste any more time. And then what I can do is, I found out in the some time back when I'm playing with this, but I forgot. So what I will do is I'll go to the first page, very first page, and delete just first 5 pages. So which is introduction part of signals and systems, and then I'll save the remaining thing, and then I will mail it to JNTUK staff so that he can mail as a PDF to all of you. So Marcel. So in time reversal, what we are trying to do is, we know that x of t has got Fourier series quotients of ak, and then what will be the Fourier series quotients of x of minus t. So we want to do this, right? So we know that, let's do this. So it's also, again, we know that a of x of t is ak e power jk omega naught t, and k equal to minus infinity to plus infinity. And what we want is x of minus t. Minus t, minus infinity to plus infinity, ak. Right, in place of t, I'm simply putting it minus t. That's it. Now, but to express x of minus t as a Fourier series expansion, what do we need is, here it should be, we should be having e power jk omega naught t, right? So how do we have this? Like how to achieve that? So we'll do a simple trick, which is put k equal to some minus m. like in any other dummy variable m. So what happens if we do that? X of minus t is equal to summation a of minus m e power j k m omega naught t. Here there is a minus m, and here I can simply remind this as m is equal to minus infinity to plus infinity. Of course, it should be minus m equal to minus infinity to plus infinity, right? But this, again, I can write this as m equal to minus infinity to plus infinity, because anyway I'm summing up from minus infinity to plus infinity. Whether I sum it from minus infinity to plus infinity or plus infinity to minus infinity, the sum remains the same, right? Whether I add from minus to plus or plus to minus, the sum remains same. So this is equal to a minus m uh, a minus m e power j m omega naught. Okay, now these are the Fourier series quotients, right? So here what we can write is, okay, we'll write in the next page, right? So what we can write here is x of minus t, it has got Fourier series quotients of a of minus k. That's it. So there are now, as an exercise or as a question, what can we do is, what happens if x of t is even it's a very simple one, so we need not have this as a question. So if x of t is even, then what is an even signal? Yep. What is an even signal? An even signal was defined by us as if x of t is same as its time reversed version. If x of t is same as x of minus t, then we call x of t as an even signal. So there is a signal and then we reversed it in time, but even then it is same as the original signal. Then we call such a signal as an even signal. So if x of t is even, then x of t is equal to x of minus t. So in that case, ak is equal to a minus k, right? So that meaning, when x of t is an even signal, its Fourier series quotients, AKs are also even. In the sense, if these AKs are, say these are AKs. This is for k equal to 0, k equal to 1, k equal to 2, k equal to 3, and so on. This is k. Minus 1, minus 2, minus 3, and so on. So this will be of something like, I'm just trying to construct an example. That's it. So So even if you flip this minus t, it will still be same. So a of k will be same as a of minus k if x of t is even. Okay, and if it is even and real, yeah. And okay, what happens when x of t is real? Okay, we'll see more of these things in exercises or in further examples. But now the fourth property. Fourth property is time scaling. So before discussing time scaling, let us recall what is time scaling. If x of t is the signal, then time scaling is x of some alpha t or x of t by alpha, right? So these are the time scaled versions of x of t. So at time scaling, either it stretches the signal along the x-axis, along the time axis, or it compresses the signal, right? So that meaning time scaling a signal will change its fundamental period. So if there is a signal and if it get compressed in time, so on the x-axis, on the time axis, it get compressed, then that means its period has what happened? The period increases or decreases? Think about it. Then similarly, a signal is there. It got stretched along the time axis, right? It got stretched along the time axis. Then period gets changed. The period either gets compressed or reduced. The period either gets reduced or increased depending on the time scaling. So before going into this property, let's recall that time scaling either time scaling changes the fundamental period of a signal. Right? Then if x of t has period t, then x of alpha into t has period t by alpha, t divided by alpha. So here alpha is we are considering it as a positive real number. See, when we scale it, we will scale it only with a positive real number. In the sense, it can be less than 1 or it can be greater than 1. Right? Hence, W naught becomes 2 pi by t by alpha, that is equal to alpha into 2 pi by t. Okay, so let me write this little bit differently. Hence, I mean the same, but the wordings are not correct. Hence, the fundamental frequency of x of t changes from omega naught to alpha omega naught. So say if x of t has got period t and fundamental frequency omega naught, x of alpha t will have period t by alpha and fundamental frequency alpha omega naught. So this is what I'm trying to say. So in such a case, what will be our Fourier series expansion of x of alpha t? See, we know that. Okay, now let's get back to our Fourier series quotients. So we know that x of t is ak e power j k omega naught t, and x of alpha t will be ak e power j k. It will be, in place of t I should put alpha t, it will be alpha omega naught t. So the Fourier series, as you can see, the Fourier series coefficients have not changed even a bit, right? So k equal to minus infinity to plus infinity. So here only the fundamental period has changed. Only this has changed, and this has not changed. AKs have not changed. Have no changed. Hence, x of alpha t also has got a Fourier series coefficient of AK. The Fourier series coefficients will not change with time scaling. Right? So simply this exponential term, this fundamental frequency changes. That's it. So the next property is multiplication. So out of all these properties, multiplication, the deriving multiplication property is the difficult one, and then we are not going to try it out right now. Right? See, you will. The reason is simply it's not only difficult. See, the difficult thing, we can spend 2 more pages on this. That's it. It's not about the difficulty, but it involves the concept of convolution. So as it involves the concept of convolution, and you haven't learned about convolution till now, the convolution comes to you as per your syllabus. It comes in your 4th unit, I guess. Yeah. So when you deal with linear time invariant systems, you will come across the concept of convolution, and then you will not be able to appreciate or understand it in a much better sense. So we'll postpone the derivation, but we'll state the result. So what if x of t, I will state this property. If x of t and y of t have the same period t, and x of t's Fourier series quotients are AK and y of t Fourier series quotients are BK, then z of t, which is obtained by multiplication of x of t and y of t. Okay, so just let's make this change of notation. let's call this as h of t. No, sorry. Let's stick with z of t. Then z of t will have its Fourier series quotients equal to Ck is equal to AL Pk minus L, where here it should be L equal to minus infinity to plus infinity. Yes. So z of t Fourier series is nothing but some Ck, where Ck is given by AL Pk minus L L equal to minus infinity to plus infinity. Right. So as I said, this summation is called convolution of AK with PK. So this is nothing but, so we will deal with convolution a little later after 1 or 2 units. Convolution of sequence AK with sequence PK. Say if you still want to derive and go through the derivation of this property, you will be able to find it in any of the standard textbooks, like not in Open Human-Vilsky, but you must be able to find it in Lathi or Simon Hagen, right? So this is the multiplication property, and then finally we have one property called complex conjugation. Complex conjugation complex conjugation and conjugate symmetry. So here it's simply we ask the question. Simply we ask this following question: if x of t's Fourier series quotients are given by AK, then what is x conjugate of t? Say we have x of t, and x of t, as we are saying, it can be complex or it can be real value. So if we know the x of t, if we know the Fourier series quotients of x of t of a given signal, then if we simply complex conjugate the signal, if we take the complex conjugation of the signal, how to obtain the Fourier series quotients? So it's again very simple to derive. So let us see this. Like, so we know that x of t is equal to ak e power j k omega naught t, and we want to complex conjugate this, right? So I'll simply, so x conjugate of t is conjugate of ak e power minus j k omega naught t. Because I have to conjugate this number, ak can also be complex, right? And you should always keep in mind that in the examples we did, AKs were real, but it need not be the case. In general, AKs are complex. So you should note carefully that only in the examples that we did in today's class, AKs came out to be the real value, but AKs in general can be complex value. So you should, whenever you take a complex conjugation of x of t, you should also take complex conjugation of AK, and you should also take complex conjugation of this e power jk omega naught. So note, AKs or complex valued in general. In some cases they may be only real values, but you should not do that mistake. So here again, let's do the trick. Let's put k equal to minus m, so that x conjugate of t is equal to m equal to minus infinity to the plus infinity, a minus m conjugate e power j m omega naught. So that implies these are the Fourier series quotients. So x conjugate of t will have its Fourier series quotients as what? As a minus k conjugate. Okay, so what do we mean by conjugate symmetry? When the title of this property is complex conjugation and conjugate symmetry, right? So the complex conjugation of is this: when you complex conjugate a signal, its Fourier series quotients not only become complex conjugated, but they also get reversed. They also get reversed in their index. So now let's assume that x of t is real. When x of t is real, we know that x of t is equal to x conjugate of t, right? For a real number, the complex conjugation is equivalent to the real is equivalent to the actual number. So when x of t is nothing but x conjugate of t, that meaning, and AK will be equivalent to, so if x of t is same as x conjugate of t, then its Fourier quotients will be same as its Fourier quotients. So the Fourier quotients of x of t are equivalent to Fourier quotients of x conjugate of t. So that meaning AK is equal to a minus k conjugate. So this is called conjugate symmetry. So that implies AKs are conjugate symmetry. So whenever this property holds, we call such a sequence of complex numbers as conjugate symmetric numbers. Right? And there is one more important aspect that comes out of from this property. So that I'm giving it to you as a question. So show that Fourier series quotients are real valued and x of t is real and even. So what I'm trying to, this you can do it as a homework. If you don't get it, you can ask me in the next class. But it is simple. You just have to use two of the previous properties, right? So what I'm trying to say is x of t is equal to x conjugate of t and x of t equal to x of minus t. Then, so what I'm asking is that if x of t is x conjugate of t and x of t is equal to x of minus t, then show that a case or real value. So we have a property for this, we have a property for this. If you use both these properties, we'll get the solution, right? So with that, we will move on to the last property, Parseval's relation. So Parseval's relation is it's generally the power relation, and as I was saying, this Parseval's relation is same as you will get this similar relation in Fourier transforms and discrete time Fourier series and discrete time Fourier transforms. So everywhere you will get this Parseval's relation. So this is one of the very important relations which you will be using it when you come to filters or whatever, like when you discuss more about systems. So this relation simply states that this relation can be stated as 1 over t integral over t x of t whole square dt is minus infinity to plus infinity. X square. So this has got some physical interpretation. So let's try to understand this rather than we don't derive this again here, and we try to derive this rather than trying to derive this. So what I mean to say is rather than trying to derive this, let's understand it. So the left hand side. So let's look at the left hand side equation. It is average power in one period. It is left hand side is average power. So why do I say average power? So this is energy per unit time. Why? See, this is the energy. Integral mod x of t square dt is the energy per unit time. So this is energy per unit time in one period, because the integral is being done in one period. In one period of the periodic signal, and then right hand side is in the right hand side, what is mod ak square? So this mod ak square, I can write this as 1 over t integral over one period mod ak square dt. So this is equivalent to this, right? You can see this integral over t is 0 to t, so t by t gets cancelled and you get the same, and this again is nothing but 1 over t mod ak e power j k omega naught t whole square dt. So the right hand side 1 mod ak square is nothing but again the average power in one period of kth harmonic signal. So on the right hand side, is the average power in one period kth so this says that the average power per one period in the actual signal x of t. So the average power in one period in the actual signal x of t is equivalent to sum of the powers in its complex exponentials. So that's what it says. Say if you look at this equation, so the average power per one period in the signal is nothing but sum of the average powers in one period in all the exponential signals, right? So with that, so okay, so let me add some more clarification here, in the sense, see these so note the quotients AKs, the quotient AK, so let's not use the plural here. The quotient AK represents, represents the strength of kth complex exponential in x of t. See, x of t we are representing as ak j power k omega naught t. So this is nothing but a naught plus a1 e power j omega naught t plus a2 e power j 2 omega naught t, and so on. Of course, we also have a minus 1 e power minus j omega naught t plus a minus 2 e power minus j2 omega naught t, and so on. So this complex exponential e power j omega naught t is getting multiplied by a1, e power j2 omega naught t is getting multiplied by a2. So what does it says is the quotient ak, so the quotient AK represents the strength of kth complex exponential in x of t, right? So this kth complex exponential is also called kth harmonic. Why do we call it as harmonic? Because see, the exponentials are e power j omega naught t, e power j2 omega naught t, e power j3 omega naught t, and so on. So they are all harmonics of the fundamental frequency omega naught t. So this is considered as the fundamental exponential signal, and this is the second harmonic of this. This is the third harmonic of this, and so on. So this term harmonic we haven't used many times in our class, right? But you will also be like, some of the questions or people will say, okay, what is the strength of third harmonic in x of t? Then you should simply say what is the power of a3. what is A3? So if a question says find the strength of third and fifth harmonics in the Fourier series expansion of x of t, then you should simply find A3 and A5, right? And what is A0? So okay, we are saying A1 is the strength of this frequency, A2 is strength of 2 omega naught free complex exponential and so on. But A0, what is A0? If you simply find A0, it's x of t dt. So this is nothing but the DC value. DC value or the average value of x of t, right? Simply over one period. Sorry, I'm not writing this neatly, but you can note this down. So A0 is nothing but the DC value. So if there is A0, that means this x of t has got some DC value. If the A0 is 0, then x of t does not have any DC value. Or it is also called the average value, averaged over one period of x of t. So this completes our Fourier series discussion. Then we will go to Fourier transforms. How do we define Fourier transforms? So the intention of the Fourier transforms is, can we also express non-periodic signals as a linear combination of complex exponentials? So in Fourier series, we have seen that x of t, if it is a periodic signal, we can express that as a linear combination of complex exponentials. So we want to try and find out whether we can also do the same thing for a periodic, for non-periodic signals x of t. So this we will do it in the next class. With that, we can complete the Fourier transforms, and then yeah, we'll take ahead from that. And if you have any questions, so as I was saying, you can email me at my email ID. I have given to you at the start of the course. So it's kvsrinivas.ece@iitbhu.ac.in.